Hello, my name is Matthew Warren, and I'm an undergraduate bioengineering student at Northeastern University. Today I'll be presenting my work on cationic drug carriers and their effects on stiffness and swelling in cartilage. Osteoarthritis is a debilitating disease involving the irreversible degradation of cartilage tissue in joints. Early intervention with disease-modifying therapeutics is imperative in OA. However, the clinical translatability of many promising drugs is limited because of challenges with their intracartilage delivery. Cartilage is comprised of a dense, fluid-filled meshwork of macromolecules that provide it with the compressive strength needed to function as a shock absorber in joints. In addition to type 2 collagen, negatively charged glycosaminoglycans, or GAGs, exist in close proximity in the tissue space. Their like-charge repulsions provide an osmotic swelling pressure that imparts compressive stiffness. Overall, this tissue structure presents a significant barrier to drug delivery. Thus, treatments for joint diseases, such as OA, critically require an efficient, rapid intracartilage delivery system. One promising delivery strategy is to utilize the tissue's negative fixed charge density. This involves conjugating a drug to a positively charged nanocarrier, which utilizes the negative electrostatic potential within the tissue and high Donin partitioning at the cartilage fluid interface to facilitate rapid transport through the full tissue thickness. Our lab has designed optimally charged cationic peptide carriers, or CPCs, for the purpose of attaching and delivering a wide range of cartilage-specific therapeutic payloads. CPCs have shown up to 400 times enhanced intracartilage penetration. However, despite their promise, it remains to be evaluated whether they affect the mechanical properties of cartilage. This is an important consideration, since perturbations to the tissue mechanical balance could compromise its ability to withstand physiological loads in the body. The goal of this work was to characterize the downstream alterations in mechanical and biological homeostasis associated with cationic nanocarrier uptake. Because of the 3 kilodalton size and highly positive charge, we hypothesized that CPC uptake would have 2 competing effects on tissue mechanics. First, swelling pressures associated with like-charged GAG repulsions can constitute up to 50% of the tissue's compressive modulus. Thus, we postulated that shielding of these charge interactions by CPCs could induce osmotic deswelling, decreasing the tissue stiffness. Second, given the very high observed uptake ratios of CPC peptides, the presence of bulk material within the tissue was expected to increase the equilibrium stiffness. We also expected the large amount of bulk material within the tissue space to reduce porosity, hindering interstitial fluid flow and lowering hydraulic permeability. To experimentally observe these charge and size-based effects, we modeled the tissue equilibrium mechanical behavior using a modified Hooke's law, which incorporates 2 concentration-dependent properties: the bulk equilibrium modulus and the free osmotic swelling stress attributed to GAG repulsions, also known as chemical stress. We began by evaluating the net effect of charge shielding of solid matrix interactions by measuring bulk stiffness of cartilage tissues pre-equilibrated with CPC of varying net charge. We performed uniaxial and confined stress relaxation testing as shown. Material parameters such as the equilibrium stress-strain relationship and the characteristic time constant tau were extracted from the data by fitting the standard linear viscoelastic model. Tissue equilibrium modulus increased following CPC uptake by up to 69%. And across CPCs of varying net charge, the magnitude of this increase showed a weak positive correlation with the CPC uptake ratio. Furthermore, using modulus and tau measurements, we applied a biphasic model to estimate tissue hydraulic permeability. We observed a decrease in permeability following CPC uptake, and the magnitude of this decrease exhibited a weak negative correlation with increased intratissue concentrations. Next, we performed real-time mechanical measurements throughout CPC uptake to independently characterize charge shielding. The osmotic swelling pressure testing regime included 2 rounds of stress relaxation, before and after CPC. Each equilibrium relationship was fit to the aforementioned modified Hooke's law, and the change in OSP for a given CPC was calculated as the difference between pre- and post-uptake chemical stress. We performed such testing with multiple CPCs using a transient state 2-hour-long static hold during uptake. Interestingly, we found that the magnitude of OSP change was higher at lower net charge. Notably, this trend is similar to reported Donin partitioning factors for CPCs, suggesting a dependence of OSP on solute uptake. Finally, we also measured changes in OSP following 24-hour equilibrium uptake, which in contrast showed increased deswelling with higher CPC uptake and charge. These measurements were consistent with theoretical calculations for CPC-induced changes in OSP, which we obtained using a macro-continuum ideal Donin osmotic model. Overall, in this study, we measured considerable changes in the equilibrium modulus, swelling pressure, and permeability of cartilage associated with cationic nanocarrier uptake. Our in vitro live culture studies using high CPC concentrations suggest no downstream adverse biological effects from osmotic changes. However, it's possible that alternative cationic nanocarriers may be less tolerable. Thus, the demonstrated methodology for quantifying changes in tissue chemical stress may be useful as an evaluative measure in future toxicity studies with charged nanocarriers. To conclude, I'd like to thank the Department of Defense, the NIH, and the Northeastern UGRCE Award for funding.